Question 13 from the 2022 National 5 Physics Examination from the SQA Section 1. A circuit is set up as shown and the resistors in the circuit are identical. And we're asked to find which row in the table shows the reading on the voltmeter and the possible readings on the ammeters A1 and A2. Now, we're not given any numbers of the current flowing, then we have to realise our own thinking about this. But the key thing is the following. We have to remember this important fact, is that if the resistors are identical, they will have the same resistance, which means the current entering the branches will halve in two. So if you've got a current coming down here of this value, maybe coming down this direction here, and it's got a value of I, then by the time it splits up into here, half the current's going to go there and half the current is going to go along there. So we're looking for A1 to be double that of A2. So let's take a look at the table then. So for response A, we have got A1 being 0.3 and 0.3. Well, that's nowhere what we're looking for. Remember, looking for A1 to be double A2. A1 here is 6 and A2 here is 3, so that's a possibility, so we can maybe tick that one at the moment. We'll have 0.3 here. 0.3 is not the case. 0.3 and 0.6 is not the case here because we know that A1 must be double A2, so that's not the case. So other possibility is this one here. So we've got two possibilities out of the 5 responses here. What's going to clinch it for us? Well, it's going to be the reading on the voltmeter. So what's going to be the reading on the voltmeter? Well, the reading on the voltmeter is exactly across this resistor here, which really is exactly the same as across this branch here, which is exactly the same as across the 12 volt supply here. So really the reading of the voltmeter will read 12 volts. So that ticks that one there. So our response to satisfy the question is going to be answer E. Now, to do these problems requires practice and building circuits. And it's not often we can build circuits, but we can go to an amazing site called PHET and we can see really what's happening. So I'm going to take you to the PHET site now, and that's it there. And that's the exact same circuit we have. You can see that we've got two identical resistors and we've got two ammeters positioned here and here, and an ammeter which measures the current coming into this branch here, this parallel branch. You can see 0.6 amps is here, and in this branch 0.3, and in that lower branch 0.3. So the current entering the branch will be double the current in each individual branch here because both resistors are the same. Now the biggest problem is, what about the voltage? Well, we can measure the voltage using our voltmeter, and first of all we measure the voltage across the branch. That's what we've been asking to do here, and you can see it's going to be 12 volts. Why is that? Because if we follow the wire around, we're just going to get the same voltage because it's connected to the same terminals of the battery. So if you measure the voltage across the battery, it's going to be exactly the same as across this branch here, 12 volts, which is going to be exactly the same as across this branch, which is going to be exactly the same across that branch. So it pays to actually build these circuits from the PHET website, which is a marvellous simulation to do. Build them up, explore them, look for the connections, and then you'll be able to answer the particular question. So to recap again, we're asked to decide which of these of the row in the table is correct, and we know that when the current is going to come down here, it's going to split in half, so A1 must be double A2. That must mean A1 is 0.6 for a guess, so it must be half of 0.6, 0.3. And the crucial one is the voltmeter across the resistor is going to measure the same as the voltmeter across the branch, which is going to be exactly the same as the voltage across the battery, 12 volts. So the answer for that one is E, but remember, practice at PHET site. Question 14. Which of the following symbols represents a thermistor? Well, you've got to know your symbols. You just got to go through each one in turn and know what they are. The first one is a speaker, and the second one is a thermistor. Always look for the rectangle, which stands for resistance, and the little hockey stick through it to show you that it's going to be a thermistor. That's the key one to remember. The third one is a lamp, and this one here is a fuse, once again a rectangle with a line through it, and the final one is an LDR, which of course is a light dependent resistor. So a good question to speed up the exam, and we know that the answer to that one is going to be B, because that's going to be the answer. That is a thermistor. Question 15. Two substances X and Y are both solid at 20 degrees Celsius. The substances have the same mass and are supplied with the same amount of energy per second. The graph shows how the temperature of each substance varies with time. Now remember, the time axis shows you the time, but in reality, because we are putting energy into it with the same rate, energy per second, really the time axis stands for the energy supplied to X and Y. So think of the time axis as the energy supplied to both X and Y. Now let's look at the statements we have to prove false or true. The student uses information from the graph to make the following statements, and we'll go through them one at a time. Statement 1. The specific heat capacity of a solid substance X is greater than that of solid substance Y. Now, to do this, we have to use some guides, and I would prefer to use little lines like this, because let's use a guide to say we're starting off at 20 degrees and we're going to raise the temperature up to 40 degrees. So we're starting at 20 and raising the temperature up to 40 degrees. So which one of those substances reaches 40 degrees first? Because if we know that it's going to take the less energy, and if it's going to have the less value of the specific heat capacity of it. So let's use our other little guide to start off the experiment in time. So remember, as the arrow moves along, it's supplying energy, and as you can see, the temperature is rising in both X and Y. But as we get to X is 40 degrees here, X has reached 40 degrees first. So therefore that must have a smaller specific heat capacity than Y, because Y takes longer time, therefore longer energy, to get to the desired 40 degrees mark there. So really what we're saying here is that substance X has a smaller specific heat capacity. So that first statement there is wrong, because it's substance Y which has the greater specific heat capacity. Why? Because it's taking longer, which means more energy, to go from 20 degrees to be heated up from 20 degrees to the desired 40 degrees mark there. That's the 40 degrees mark. It's just reached it. So the first statement is wrong. Let's take away our little guides and look at statement 2. Substance X changes state at a higher temperature than substance Y. Well, let's take a look at the flat line here. This is a place where the temperature no longer rises. This is where the substances are changing state. Remember, you can put a lot of energy in and it doesn't show up in a temperature rise. It just shows up in a change of phase. And remember, the length of this line here, according to our graph, is really the amount of energy needed to make that change of state. But you can see substance X changes state, if we slide it along, to about, say, 50 degrees. And substance Y, if we go along that flat line and move it along to temperature, that changes state at the beginning of 40. So we're correct in saying that substance X is going to change state at a higher temperature. You can see it's changing state area there, and that corresponds to a temperature of 50 degrees. So statement 2 is going to be correct, because substance X changes state at a higher temperature than Y. So that's going to be our correct statement. Now our third and final statement is about the specific latent heat of fusion of substance X is greater than that of substance Y. Well, let's see how much energy was needed to change X completely from a solid to liquid, and we can do that once again with our little line here. We place the line across here, and remember, the length of that line is going to be the length of the time, which is directly proportional to the energy supplied. So you can see that the specific latent heat of fusion for this one is that length there. And let's compare it with substance Y, and you can see substance Y's length is actually slightly shorter. So substance Y has got a less value of specific latent heat of fusion. Just to check that again, you can see the line place it on the flat part of the graph. That's the place where the substance X is changing state from a solid to liquid, and the length of it is really the amount of energy needed to completely change that from solid to liquid. And you can see it's going to be shorter than substance Y's. So the specific latent heat of fusion of substance X is in fact greater, it's a longer line than Y's, is greater than that of substance Y. So we can give that a tick as well. So there's the two statements that are true, statement 2 and 3, and that's going to correspond to response D.